Hello everyone, welcome back. Today we are going to understand one of the most important topics in networking, spanning tree protocol, which is also known as STP. If you ever wondered why networks crash due to loops, why switches forward packets infinitely, or how to keep redundancy without bringing down the whole network, STP is the hero behind the scenes. Now let us break down it in a very simple and visual way. Imagine we have two switches connected with just one cable. It works, but we have a single point failure. If that cable goes down, complete networks breaks down. So what do we do? We add a single second cable to give the redundancy, but the moment we add the second cable, oh, we have just created a complete network loop. And trust me, loops are really very deadly in switching. See, we have connected the second cable. As a result, redundancy has increased, whereas again the loop created. So we will see with an extra cable, we are now have redundancy. So unfortunately for us, redundancy also brings a loops. Why do we have a loop in this scenario above? I'll explain you it in a very simple way. H1, this host 1 sends an ERP request because it is looking for the MAC address of the H2. An ERP request is a broadcast frame which is being sent. So SW1, what it will do, it will just forward this broadcast frame on all the interfaces except the one which is where it has been received. Similarly, SW2 will receive both broadcast frames. Um, Now, what does SW2 do with this broadcast frames? It will forward it from every interface except where it has come from, which means that the frame which has been received by on FA 0 bar 0 will be forwarded on interface FA 1 bar 0. The frame which was received on 1 bar 0 will be forwarded on interface FA 0 bar 0. So this process will keep on doing infinitely, which we can see that very clearly we have a loop. Both switches will keep forwarding over and over again until whether we fix the loop by disconnecting one of this cable or one of the switches go into crash because they are being strained much, which means stressed much, overburdened with the traffic. This is happening because Ethernet frames do not have a feature called as TTL, time to live value. So they will keep on looping around forever. Though besides ARP request, many frames are broadcasted. Example, whenever the switch does not know about a destination MAC address, it will be flooded. So this is the very biggest problem when we don't have something called as the STP. How this STP will solve this particular problem? Spanning tree problem will solve the loops. How it is getting solved, we'll see. Spanning tree protocol will help us to create a loop-free topology by blocking certain interfaces. See, if suppose I'm blocking one of the interfaces, then I will not have a loop. The loop will be disconnected. But we need to do it in a very proper way. We have three switches. So we have three switches. I'm taking this SW1, SW2, and SW3, and each switch is having its own MAC address. And switch 1 is having MAC address of AAA, and switch 2 is having MAC address of BBB, and switch 3 is having the MAC address of CCC. We have added the redundancy by connecting the switches in a triangle, which means once we connect it in a triangle, which means we have a loop here. We have added the MAC addresses, but for making it a simplification, do not take it in a very complex way. I have given explanation based on the simple MAC address, for example, AAA, BBB, and CCC. Since spanning tree is enabled on all the switches, it will send a special frame to each other like in hello packet called as the BPDU, which is nothing but bridge protocol data unit. In this BPDU, there are two pieces of information. One is all about the priority, other one is the MAC address. And together, priority and MAC address will form something called as the BPDU GOD, bridge protocol data unit, which is called as the BPDU. It is sent between all the switches. You can see here BPDU is sent between these switches, and these switches. It will keep on sending it. And spanning tree will require the bridge ID for its calculation. First, what it will do, it will elect a root bridge. This root bridge will be the one of the best bridge ID, which is like a superhero. So one among these three switches will become a root bridge. For calculating the root bridge or electing a root bridge, the switch with the lowest bridge ID will be the best one. Normally by default priority is 32768, but it is possible to change this value when we want. I'll explain you when actually we need to change this priority ID. So who will become the root bridge? So in our example, SW1 will become the root bridge because if you say take the priority is same for all the switches, so I cannot go with the priority value. Second, I'll go with the MAC address. See, MAC address is A, which is least comparing to B, C, or C. Since it is having the least MAC address, it is having the best option. So SW1 will become an root bridge. See, I have noted here. We have elected our king because here we have the root priority ID is the same, whereas MAC address is very less. So the ports which are on our root bridge, those ports are called as the designated ports or root ports. These are called as the designated ports or the root ports. You see, when the SW1 is elected as the root bridge and the interface is D stands for designated here, we have kept since they are near our root bridge, we are making them as the designated ports, which means all the traffic should flow either in this way to this port or to this port. That is why these two ports are called as the forwarding ports, or they are called as the designated ports. And now we have agreed that root bridge. Our next step is to find out which are non-root bridges. Okay, so that every switch that is not the root will have to find out the shortest path to route our root bridge. Um, See here, the ports, the shortest path to reach the root bridge is called as the root port. So this is the shortest path here to reach the root bridge, and this is the shortest path from here. So this is called as the root ports. So we have got the designated ports and the root ports. We got both. Then if we have put, I have put R for just root ports on SW2 and SW3. So that FA 0 bar 0 interface is the shortest path to get into the bridge. In this example, we have kept it very simple, but the shortest path in spanning tree means it will actually look at the speed of the interface. So in the case of fast Ethernet cable, it is cost 19. Like that, it is depends upon the which type of cable we are actually using it. I've given here based on the speed, what is the cost which is being taken. Each interface will have certain cost, and their path which is the lowest cost will be used. Here is the overview of the interfaces and their cost. I've given it for the reference. Now we have designated ports completed, and we have completed our root ports also. Then one of the ports should be designated, or one of the ports should be blocked. Only in that case I'll be able to avoid the loop. How to do this one? Now I'll compare the MAC addresses of here non-root 1 SW2 and SW3. I could see that comparing to B and C. So this is having the least MAC address, which is having the best priority. So I'm making this port as my designated port, and this port I am making it as the blocking port. So this port is going to be the blocking port because this port is having the highest MAC address. So bridge ID, as I told you, it is priority ID. Priority plus the MAC address is called as the bridge ID. So now we have done with that. Okay, this is the alternate port. So I am blocking this alternate port, or it is also called as the non-shedding port. And this process completely, we are not doing it. Spanning tree protocol will do complete process. It will do with the help of three states. The states are nothing but listening, learning, and forwarding or blocking state. Here, the port is in listening state for almost 15 seconds. Then in this phase, it will receive and send the BPDUs as we discussed, and still neither learning MAC addresses nor data transmission. Whereas when it comes to next 15 seconds, it will start into the learning stage. The port will be in learning stage for next 15 seconds. We are still sending and receiving the BPDUs, but now the switch will learn the MAC addresses. Okay, still no data transmission will be happening here. Then next, it will decide upon which is going to be forwarding or blocking state in another 20 seconds. It will take whether it is to be gone to forwarding or blocking state. So together we will have 30 plus 20, 50 seconds we need to do it. This we can avoid using a command called as spanning tree port first. We will see that using the how to use that, where to use this spanning tree port first command during the implementation process. To summarize what we have discussed so far, why do we need STP? Switch loops cause broadcast storms and network crashes. So STP will prevent the loops by blocking the extra links. The root bridge elected based on the lowest bridge ID, and non-root switches chooses the root ports, and STP will select the designated ports and the alternate ports, and ports will move through blocking, listening, learning, and forwarding in this way. Here are the common, sorry, hey, one more thing is there for that. Okay, I need to thank that website networklessons.com from where I could able to take this content. Um, See, these are some of the show commands which we can use it. Show spanning tree summary, show spanning tree detail, show spanning tree root, and show spanning tree bridge. These commands will help you to understand which is the root, which ports are forwarding, and which ports are blocked. All these things we can discuss. Um, then we will discuss about the implementation portion and further things like port pass commands in the upcoming video on spanning tree protocol implementation using the PNETLabs. Thank you. If you have any doubts, you can put a comment in the comment box. Or if you want similar videos, you can just type which type of video you want in the comment box as well.